Built up our idea of analysis of variance. We said the point of the test was to compare the means for several groups, yet the name of the test involves variance. We pointed out we have two layers of variance to look at. The between sample variance, so between these three different groups, it looks like there's some variability in recovery time after knee surgery. And then the within variability, so scenario A, we saw that represented more consistent differences, whereas scenario B, within each group, it was kind of spread out and random and had a lot of variability. So we need to consider both layers of variability to determine if these differences are likely to represent true differences in the population. So let's introduce some terminology and notation for these ideas. So here, we're going to describe these two layers of variability. The layer of variability between the groups is going to be measured by a quantity called SS factor. Or sometimes you might see it called SS group. So how much is that factor or that grouping variable contributing to the difference? So in this example, SS factor compares our group means, that X bar for below average of being 38 days, the average being 32, and then the above average being our 24 days. So the between variability is measured by this quantity, SS factor, or SS group, and it's comparing just the averages for the three groups. Do they look different or not so much? The within variability, so that's our scenario A versus B. Is it consistent differences or are they kind of random? This one is measured by SS error. If you see this in software other places, it might be called SS residual as well. And in our example, SS error, if we looked at our two scenarios, which one would have a larger SS error? Yeah, the second scenario, scenario B, because there was a lot more variability within each group in that particular setting. So in our example, SS error would be larger in scenario B. Now, let me pause for a moment. I keep using this notation, SS factor, SS error. That doesn't stand for Secret Service or anything really cool like that. SS stands for sum of squares. So SS equals sum of squares. And in this class, we're not going to worry about using giving you the formulas for these. We're going to use our calculator to do all this, but I want to give you a little bit of intuition on what's going on, how we're developing the test. So basically these sum of squares, what they're doing is they're summing up observations from the mean. The details of what observations and what mean depend on if they're talking about between or within variability, but they're summing up these squared distances of points to the mean. Okay, so that should look really familiar. This should make you think of, hey, this is kind of the numerator part of our formula for variance. Now we're getting closer to why this is called analysis of variance. Here's the numerator part of that formula for variance. That's what these sum of squared terms are. One is for comparing the variance of these three numbers. The other one is the variance within in the groups. Is it a big variance or a little variance? So all this information is going to be summarized in what we call the ANOVA table. So no matter what software you use, it's going to output a ANOVA table. and it's going to be pretty similar with every software. So let's look at our ANOVA table. The first piece of information we have is the source of variability. So when we're talking about the source of variability, we can have variability coming from our factor. Okay, how much of the differences are due to the fact that we have different factor levels, different prior fitness levels. We also have variability that can be just random. Even though I'm looking at within a factor level, there's still random error and variability. If I add those two together, I should always get the total variability. So we're going to label our rows here. Is the variability coming from the fact that I have 3 fitness levels, or is it random error within and that variability within the factor levels? When I add those two sources together, I get the overall total variability. Now the next piece is our degrees of freedom. So our degrees of freedom, you can think of it as kind of our n-1 in a way. Okay, so for the total degrees of freedom, it is actually n-1, total number of observations minus 1. For our factor, we can think of it as n-1, but our n is the number of things we're comparing, in this case, number of factor levels. So here, I'll say number of factor levels minus 1. And don't worry, we'll fill this in for our example in just a little bit. So this is like our n-1, how many factor levels, minus 1. And then error is a little bit trickier to remember. You can remember that these two have to add to the total. That might be helpful. So that would give us n minus number of factor levels would give us the degrees of freedom for error. And if you want to think about it over here, where it's coming from is we're looking at the variability or the error within each group. So I have these points minus 1, these points minus 1, these points minus 1. So when I add them all up, I get total number of points, but I've done a minus 1 within each group, so minus the number of groups. That's where that's coming from. But either way, you want to remember it. These guys add up to the total, or kind of remember the picture, the reasoning from the picture. All right, let's check out the next column is our sum of squares. So we mentioned those earlier. So this one is our sum of squares for the factor. And this value is going to tell us variability explained by the factor. Okay, so how much of it is due to my 3 fitness levels? I'm comparing the means across those 3 prior fitness levels. The next one is our sum of squares error. And this guy is our unexplained variability. So variability unexplained by the factor. And let me maybe just point that out in our picture up here. That was the variability within each group. So that's like saying, okay, I'm checking out all these people with above average fitness, and they still don't have the same recovery time. There's still something I can't explain. Still, some people take less than 24 days. Some people take more than 24 days. There's still unexplained differences, even though I'm already looking at people that all have the same physical fitness level. So that's what our SS error is measuring, variability unexplained by the factor. And then this guy, our SS total, is actually just the variability of the whole data set regardless of the factor. So I'll just say overall variability in the data. Okay, so regardless of factor level, just overall, how much does it vary? And same thing, the sum of squares factor plus sum of squares error must add up to the sum of squares total. So I'm going to make a little note down here that these two columns are additive. These two columns, none of the other ones are, so don't try it. These two columns are additive. And specifically, what we mean by that is SS total is equal to SS factor plus SS error. That might be helpful in figuring out some of these values. Okay, next column is going to be MS, and that stands for mean squares. So let's go back and remember what we defined SS as a moment ago. We said SS was our sum of squares, and it looked like this, summing up the squared differences of some points to some mean. And we mentioned, hey, that looks kind of like a variance. So mean squares is going to be our sum of squares over its degrees of freedom. So that's going to look like, maybe I'll call this as an example. So that's going to look like that sum of squares over its n minus 1, which is the variance. So this is our variance calculation, the sum of squares over its degrees of freedom. If you have a highlighter handy, you might want to highlight this idea, and we'll write it in the table in a moment. But mean squares is making this sum of squares kind of a mean or an average by dividing by the degrees of freedom, which gives us a calculation for variance. So MS, mean squares, so we've got mean squares factor is going to be equal to sum of squares factor over the degrees of freedom for the factor, which was number of levels minus 1. Then we've got mean squared error, and that's going to be our sum of squares error over our degrees of freedom for that, so n minus the number of levels that we have. And then finally, the mean squares total, we never use this for anything, so don't write anything there, just leave it blank. These two, now that we've done this division, they don't add up to mean squares total, just forget that value. Leave it blank in the chart. All right, next part, we're going to calculate our test statistic. So F is going to be our test statistic. And this is going to be calculated by taking our mean squares for the factor and dividing by our mean squares error. Now, I'll do one more equal to kind of remind what this ratio is representing. Remember, the factor is telling us how much variability is explained by our variable, by our factor. So, explained by the factor. And our denominator, the error, is saying, hey, even though I'm looking within a certain factor level, there's still differences I cannot explain. So our denominator is this unexplained random variability. So unexplained by the factor. So that's our test statistic, this ratio of how much is our factor telling us versus how much is random. So think about it. If our factor is really important in controlling the response or the outcome, then the numerator should be much bigger than the denominator. If the factor's not telling us much and most of the differences are unexplained and random, then the denominator is going to be a lot bigger. So the ratio of the numerator and denominator give us an idea of which one is kind of controlling the setting, the factor or randomness that's telling us the factor doesn't play an important role. Now, the next entry, just leave as blank. We don't have anything there or here. So there's only one number right here, our test statistic. And we're calling this F. It doesn't look like a z-score anymore. It looks very different from that. All right, we might be running out of room here. Our very last column is actually finding our p-value. And we'll use our calculators to find this, or it'll be given to us. So don't worry about actually finding that number, but I'll just, and then after that, these guys are empty. Nothing to put there. But I do want to think about our p-value for a moment. Our p-value is coming from the test statistic, and this distribution is not a t distribution, not a z distribution, because we called our test statistic F, so it's now an F distribution. So let me draw a picture here, our F distribution. Think about Z and T. Those are both look like kind of that bell curve. Z and T were kind of this bell curve centered at 0. I could get negative and positive values. If you think about this ratio, what kind of values am I not going to be able to get? Sure, I can't get negative values because I have sum of squared numbers on the top and on the bottom. So I have positive over positive. I'm never going to get negative. So if I use Z or T, I'd be kind of wasting a whole half of a distribution. So the F distribution starts at 0, kind of looks like this. It only takes on positive values, which makes much more sense with our test statistic that we're using. All right, in the next couple videos, we'll look at some examples and get a feel for this. I know it's overwhelming at first glance, but the more you practice, I think you'll feel pretty comfortable with these concepts. So grab your calculators and let's try an example.